In this video, we discussed learning outcome number 1, which is all about testing a claim about a mean when the population standard deviation is unknown. Here we're going to talk about 3 methods: the critical value method, the p-value method, and the confidence interval method. I want you to be familiar with all of them and comfortable with all of them. In all 3 cases, we're going to use the student t distribution. My hope is by the end of this video, you'll be able to describe how all 3 methods are equivalent to each other and why each method will lead to the same conclusion. So first, let's talk about the p-value method and the critical value method. Sometimes the critical value method is called the traditional method or the classical method. I just wanted you to be aware of that terminology in case you see it in your homework. Okay, so here's some notation. Remember, lowercase n represents the sample size. X bar is the sample mean. Usually that is a particular sample mean for our sample. Lowercase s represents the sample standard deviation. Lowercase sigma is the population standard deviation. In this video, we're talking about testing a claim about a population mean when this population standard deviation sigma is not known. And this mu sub x bar is the mean of the sampling distribution of sample means. Now, I know that that's got a lot of different words, all involving samples and means. Let's break that down a little bit. Remember back in 6.3, we talked about sampling distributions of different estimators. And we said that X bar is an unbiased estimator of that true population mean. So X bar is the sample mean. And basically, when we're coming up with this sampling distribution of sample means, what we do is we pull a sample of size lowercase n, maybe n is 100. So you select 100 values, and then you compute a sample mean. And then you select 100 other values, and then you compute a sample mean. And you do this over and over again until you have a lot of different samples, all of the same size, and you have an X bar for each of them. If we look at the distribution of those sample means, those X bars, the mean of that distribution of the X bars is notated by this mu sub X bar. So this is the mean of the sample means. And just a mu by itself represents a population mean. We're going to use the notation t sub test for a test statistic. This is the t-score corresponding to our sample mean X bar, and that t-score comes from the student t distribution. And then the last one we'll look at is t sub crit for the critical value of t. This is also from the student t distribution. This is a particular t value that separates test statistics t that are significantly high or significantly low from test statistics t that are likely to occur due to chance, given that the null hypothesis is true. Now, t sub crit, the critical values of t, critical value or values of t, will depend on the significance level that we've chosen for our hypothesis test. Okay, so here's the procedure for testing a claim about a mean when the population standard deviation is not known. Sometimes this is just called a t-test. So if somebody asks you to do a t-test, what they're asking you to do is to test a claim about a mean. First, we want to check the requirements. We need to have a simple random sample, and then one of these conditions or both of these conditions need to be satisfied. Either the original population is normally distributed, excuse me, or the sample size is greater than 30, or both. When these are met, then we know that the sampling distributions of the sample means has a student t distribution. So using the student t distribution would be appropriate here. Now, we say that this t-test is robust against departure from normality, which just means that the test works reasonably well as long as the departure from normality isn't too extreme. So if the population is normally distributed, or n is greater than 30, or the distribution looks approximately normal, but it might not be normal, but it's not too different from that normal distribution, then it turns out that this t-test is going to work just fine. That's what that robust against departure from normality means. Okay, so after you've determined that the requirements are satisfied, you want to state the claim in symbolic form and then use it to infer the null and alternative hypotheses. And then we want to identify the sample size, sample mean, and sample standard deviation. Often those are just given to us in the problem statement. We call those summary statistics. Sometimes someone will give those to you, or sometimes they'll actually give you the sample, and then you'll need to compute the sample size, the sample mean, and the sample standard deviation. Then once you have all of those summary statistics, I'll want you to graph the sampling distribution of the sample means, assuming that the null hypothesis is true, and then label the sample mean for our particular sample on the graph. The question is, if the null hypothesis is true, is the sample mean from our sample significantly high or significantly low? If it is, so we've got this rare event actually happening in reality, we might say, the assumption that led to us concluding that this event is rare must be false if it's actually happening. So let's reject that assumption, which means we're rejecting the null hypothesis. And then we'll use the fact that we're rejecting the null hypothesis to state something about the original claim. So that's the main question. If the null hypothesis is true, is the sample mean that we have from our sample significantly high or significantly low? In order to answer that question, we need to compute the test statistic T corresponding to that sample mean. And then we can use that test statistic to make a decision about the null hypothesis. Now, first, we're going to talk about two ways to do that, the p-value method and the critical value method. So our first option is the p-value method. Now, the p-value method has this one downside. In order to find p, we're going to have to use technology. That's because we're using the student t-distribution, and the student t-distribution is different for different sample sizes. So if I want to find that p-value, which corresponds to an area in one tail or possibly the sum of areas in two tails, in order to find that, I'm going to need to use technology to find that. Because every student t-distribution is different depending on the sample size. But once you find the area in the tails, p-value, then you're going to compare it to your significance level alpha. If p is less than or equal to alpha, that means that having a test statistic t as extreme as our test statistic, or more extreme than that, is less than or equal to alpha, the significance level. So the probability of getting a test statistic like ours is very low compared to the significance level alpha. If p is low, then we reject the null hypothesis. You remember that mnemonic that we used earlier this semester. We said if the p is low, the null must go. And that's just a simple mnemonic to remind us that when p is less than alpha, we're rejecting the null. But I would love it if you could think of that in terms of the rare event rule rather than using that mnemonic. Now, if p is greater than alpha, we'll fail to reject the null hypothesis. So that means that the chances of getting a test statistic as extreme as our test statistic or more extreme than our test statistic are relatively high, given that the null hypothesis is true. Or in other words, values of the test statistic like ours are likely to occur due to chance, given that the null hypothesis is true. So at this point, we can't say we accept the null hypothesis. We can't prove that the null hypothesis is true, but we can fail to reject it. We can say the null hypothesis might be true. And again, we could use a mnemonic. If p is low, the null must go. If p is high relative to alpha, the null can fly. That's our little memory device there. Okay, so you've got the p-value method. That's one option. Now, if you don't have access to technology, you can use the critical value method instead. In order to do this, you need table A3, which you'll have access to during your exam. So what we'll do here is we will identify the degrees of freedom of our particular data set. And then once we have the degrees of freedom, we will use those to find the critical values of t on table A3. And then we'll use those critical values or value to sketch the critical region. And then we want to graph our test statistic on the same graph. And the question is the test statistic in the critical region or not? If the test statistic is in the critical region, then that test statistic is significantly high or significantly low. So we're going to reject the null. Or in other words, if the absolute value of the test statistic is greater than the absolute value of the critical value of t, that means that test statistic is farther out in the tails, which means it's in the critical region. We'll reject the null. You can either use this first method where you graph the critical region and graph the test statistic, or you can use this inequality, but they're equivalent to each other. Now, if the test statistic is not in the critical region, or if the absolute value of the test statistic is less than the absolute value of the critical t-value, then we fail to reject the null. Okay, so after we've done that, we've come to some conclusion about the null hypothesis. We always want to state our conclusion about the original claim in non-technical terms. We don't want anyone to have to take statistics to understand where we're coming from. People don't know what null hypotheses are. It's not necessarily common knowledge to understand what a test statistic is or what the student t-distribution is, but we want to be able to explain the results of our study in terms that everyone can understand. So that's what we'll do in step 7. Okay, so I just wanted to review on this slide the test statistic, p-values, and critical values that we use whenever we're testing a claim about a mean when that population standard deviation is not known. Here we're using the test statistic t, and remember this is a t-score that corresponds to a sample mean x bar. We're doing this provided that the sampling distribution of x bar is approximately normal, and the mean of the sample means is equal to the population mean that we're assuming in the null hypothesis. So that's giving us a t-score associated with x bar, assuming that the null is true, from a student t-distribution, and that student t-distribution will have n-1 degrees of freedom. This allows us to determine if x bar is significantly different from the mean, significantly high or low, provided that the null is true. Now, in order to find our p-values, this is where we're going to have to use technology. So you could use Excel, you can use a TI-83 or an 84, excuse me. You can use StatCrunch or Minitab or many of the other software packages that are available. I'm just going to show you how to use Excel because almost everyone has access to Excel. And as a TCC student, you have free access to Excel. So these are the 3 functions that we will use in order to find the area and the tails for the p-value method. And then for critical values, you have the option of using table A3, or Excel. We're going to focus on using table A3 here and use the critical value method when we don't have access to technology. But you should know that we could use Excel to find the critical values as well. And I think I will show you how to do that at least once so that you are aware of how the critical value method can be used with technology if necessary, or not necessarily if necessary, if you want to. Okay, so in order to do that, or before we do that, let's review some key features of the student t-distribution. Now remember, the student t-distribution looks a lot like the standard normal distribution, but it has slightly different shapes for different sample sizes. So here's a graph. This green curve here is our standard normal distribution. Now when n is equal to 12, we've got this red graph here. Or I guess it looks kind of maroon. It's really close to the standard normal distribution, but notice it's a little bit shorter. The y values are a little bit smaller, and it's spread out a little bit more. And then when n is equal to 3, we have something that's spread out even more. So they all have the same basic shape, but the y values are different, which makes it a student t-distribution as opposed to a standard normal distribution. So we have that same bell shape, we see the same symmetry, but we see that it also has greater variability, or in other words, it's more spread out. And that's to be expected whenever we have small samples. If I'm only choosing 3 values or I'm choosing 10 values, and then I am looking at means of 3 values or 10 values, well, I would expect to have more variability in those means if I'm only choosing 3 values from a data set than I would if I were choosing 10 values. Or if I'm choosing 100 values, I'm going to have even less variability. So when we have small sample sizes, we're expecting more variation, and that variation is expressed in the spread of these student t distributions with different that are associated with different sample sizes. Okay, so if our population has a normal distribution, then if you compute a bunch of sample means, X bar, um, and then you subtract the population uh, mean, and then you divide by the sample standard deviation divided by the square root of n, that's going to be a new random variable, that's t. If you look at the distribution of that, you get what's called a student t distribution. This is sometimes just called the t distribution. It's called the student t distribution because of some history that we talked about back in 7.2. If you want to see how these graphs change for different values of n, you can just click here and it'll take you to the Desmos interactive graph. Okay, so we just talked about this. It has a same general shape. It's a bell-shaped curve, but it's wider. It's more spread out. And that's what we would expect whenever we have small samples and we're computing means with small samples. The mean of the student t distribution is 0, which is similar to our standard normal distribution, but the standard deviation of the student t distribution varies with sample size, but it's always greater than 1. With a standard normal distribution, the standard deviation is equal to 1. With the student t, it's greater than 1. Again, that's another reflection of it being more spread out. And we see that as the sample size gets larger, the student t distribution gets closer and closer to that standard normal distribution. Okay, now, whenever we computed confidence intervals using the student t distribution in chapter 7, this was confidence intervals for means, for population means. We computed what was called a critical value t sub alpha over 2. Now, this serves the same purpose as the critical value z sub alpha over 2, but it takes on different values, y values, because the student t distribution, depends on the sample size. So the value t sub alpha over 2 is going to separate that top alpha over 2 area under the curve from the rest of the area under the curve. Just for example, if n is equal to 15 and we're dealing with a 95% confidence interval, t sub alpha over 2 turns out to be 2.145. Let me show you a graph. If we're talking about a 95% confidence level, then we're interested in this 95% of the area in the middle of our student t distribution. The remaining 5%, that's typically called alpha, that's going to be split into the two tails. Since I've got 5% that I'm splitting into two tails, I've got 2.5% in the left tail and 2.5% in that right tail. T sub alpha over 2 is that t-score that separates that top 2.5% from that bottom 97.5% of the area under the curve. Now, it turns out that that t value is 2.145. I wanted you to see on this slide that the t sub alpha over 2 and the z sub alpha over 2 basically do exactly the same thing, but you get different t values. So when n is equal to 15 and you've got a 95% confidence level, our t sub alpha over 2 is this 2.145. Now, if you are looking at a 95% confidence level for a standard normal distribution, the graph is similar. You've got 95% of the area under the curve in the middle. You've got that 5% of the area split into two tails. You got 2.5% on the left tail, 2.5% on the right tail. So the graphs are almost identical. But here with the standard normal distribution, z sub alpha over 2 is 1.96. So that z-score separating the top 2.5% from the bottom 70 or 97.5% is 1.96, whereas the t-score for n equals 15 for that particular sample size that separates that top 2.5% of area under the curve from the 97.5% of area under the curve is 2.145. So you see it takes on the same role, it plays the same role, but it's taking on different values. In this slide, we discuss degrees of freedom and interpreting the critical value T sub alpha over 2. Now, since the student T distribution is different for different sample sizes, we need to make sure that we choose the correct one. Rather than associating a student T distribution with a sample size, it tends to be associated with a number of degrees of freedom for our data set. Now, the number of degrees of freedom are the number of sample values that can vary after certain restrictions have been imposed on all data values. In our context, the degrees of freedom is going to be the sample size minus 1. So in our context, the degrees of freedom are the number of sample values that can vary from our sample. So if we're selecting values from the sample, we're saying how many of them can we select? Well, if we have n values to choose from, we can select n minus 1 of those values. So that's why the degrees of freedom is n minus 1 this time. I always like to think of this in terms of softball or dodgeball or any of those team sports that you may have been chosen for in school. I always think of this nobody likes being picked last idea. But the idea is this: as people are choosing teams, like you've got one kid picking members for his team and you've got another kid picking members for his team. And someone says, okay, I choose that one and I choose that one and I choose that one. If you have n kids to choose from, well, people can choose n minus 1 of them. But then there's that last one who just sort of ends up on the other team by default. He ends up on the last team by default. So that's that getting picked last. That's exactly what we're talking about here, but rather than talking about kids being picked for teams, we're talking about sample values. If we've got if we have n sample values, we can choose n minus 1 of them, but then there's going to be this one left over that we're kind of stuck with. So the degrees of freedom are the number that we can choose. Okay, let's apply what we just learned in an example problem. So the problem statement says, students of the author, that's the author of our text, Mr. Triola, estimated the length of 1 minute without reference to a clock or a watch, and the times in seconds are listed below. So one student waited 69 seconds and said, I think that's 1 minute. And another student waited 81 seconds and said, yeah, that's 1 minute. One student said, after 39 seconds, that's a minute. And so on for all of these different students. So you've got all of these different times. And these are estimates of students how long a minute is, just very subjectively. We're asked to use a 0.05 significance level to test the claim that these times are from a population with a mean that's equal to 60 seconds. Here we want to use the p-value method and the critical value method and show that we get the same result either way. So first, we're going to check the requirements. We can assume that the sample is a simple random sample. Now, the second requirement is that the population is either normally distributed or the sample size is greater than 30. Now, we didn't count all the values. Let's count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We've got 15 values. Well, that's not greater than 30. So we have to determine in some other way whether the sample data appear to be from a normally distributed population. One way that we can do that is we can graph a histogram. So what I did was I went online and I just Googled free histogram maker, and I entered those 15 values in a free histogram maker and came up with this graph over here. This shows what appear to be normally distributed data. We've got that high-low or low-high-low pattern. There is symmetry about the middle. So that distribution looks approximately normal. So based on the distribution that we see when we graph that histogram, we're going to assume that the second condition is satisfied. Remember, it doesn't have to be a perfectly normal distribution. It just has to be approximately normal because the t-test is robust against departures from normality. Okay, so our requirements are met. Now we want to state the claim in symbolic form and use it to infer the null and alternative hypotheses. In the problem statement, it said use a 0.05 significance level to test the claim that these times are from a population with a mean equal to 60 seconds. Or in other words, that the population mean is equal to 60 seconds. That's our claim. Now, since it has an equal sign in it, that means it's the null hypothesis. If that is not true, then the mean would be not equal to 60 seconds. That's the alternative hypothesis. Now we want to identify or compute the sample size, the sample mean, and the sample standard deviation. Our sample size is n equals 15, and our sample mean turns out to be 940 over 15. We just add all the x's together and we divide by the sample size, and that's approximately 62.667. In Excel, if we wanted to find the sample mean, we can use the average function. And then to find the sample standard deviation, I could use this formula from back in chapter 3. So we take every x value, subtract the sample mean, that's giving us a deviation from the mean, and then we square those because we want to count all the deviations from the mean as positive. And then we divide by that n-1, that's the number of degrees of freedom in our sample. And if we take the square root of that, that gives us the sample standard deviation. That turns out to be 19.481. Another way that we can find that is to use STDEV, that's standard deviation, .s for sample standard deviation in Excel. So I'll show you how to do that now. Okay, so I've entered the data in Excel. If I want to compute the mean in Excel, I just type an equals sign. And then one way I could do it is I could add up all those values. So we'll use the function sum, S-U-N, S-U-M, open parentheses, and then you want to select all of the cells where your data are. So I want cells A1 through A15. I use a parent over there on the other side and then hit enter. That gives me 940. And then I want to count the number of values. We already know that that's 15, but you could use the count function in Excel to count those values if you wanted to as well. So I want to count all the values between A1 and A15. We know the answer is 15. And then the mean should be the sum divided by that count. Oops, it's not letting me select that cell. Let's do it down here. So you get that 62.667 and so on. So that is one way to compute the mean, or you could just use Excel's average function. Average is Excel's name for the arithmetic mean. So I want the average of the values in A1 through A15, close parentheses, and see we get the same answer. I'm just going to highlight all of these to remind myself that my data are actually up here. Okay. Now, we also talked about on this slide finding the sample standard deviation. So in order to find that, I could take each x value, subtract the mean, square those, add them together, divide by the degrees of freedom, and take the square root of the answer. Let me show you how to do that in Excel. So I'll go here, select the x value that I'm interested in, and subtract the mean, which is actually way down here. So it's in A19. So hit enter. And that gives us about 6.333. Now, if I want to subtract the mean from all of these values, I can't just drag and drop, because what it'll do is it will take A19 and Excel will replace it with A20 in the next cell, and then A21 in the cell after that. See, it says A20 there and A21. That's not what we want. In order to get it to do what we want it to do, we need to tell Excel that we want this first one to vary as we drag and drop, but we don't want the second one to vary. To force the second value to stay the same, you put a little dollar sign in between the A and the 19. That's just going to ensure that we use A19 the whole time. So I'll drag and drop now. And you should select a cell, and you see this one is giving me A10 minus A19. So that's giving me this X value minus the mean, which is what we want. Okay. Actually, let's add a row here. So these are our X values. These are X minus the mean. And now here I want X minus the mean squared. Okay, so I'm going to type equals, select that X minus the mean, use caret2 to square it, hit enter, drag and drop. This is much faster than it would be if you were doing it by hand. And then we want to sum those. So I will take the sum. So I'll say equals sum, open parentheses, and select all of those cells. And then I want to take that and I want to divide by 1 minus the sample size, which is 14. And then I want to take the square root of the answer. That is my sample standard deviation. So I get a sample standard deviation of about 19.4813, just using the formula, or we could just use the built-in sample standard deviation function in Excel. So we could type equals stdev.s, open parentheses, and then select the cells that we're interested in. And see, I get the same answer either way. So you can use Excel's average function or Excel's sample standard deviation function if you want to, or you can do what we did here. You can use Excel to actually do the computation. Okay. So now we've got the sample size, 15, the sample mean, which is approximately this 62.67, and then we've got the sample standard deviation was about 19.48. Now we want to graph the sampling distribution of the sample mean, assuming that the null hypothesis is true. And remember, the null says that the population mean is 60 seconds. And then we want to label the sample mean that we actually obtained from our sample on that graph. So remember, when you're looking at a sampling distribution of the sample means, the mean of the sample means is actually equal to the true population mean. And this time, whenever we draw this, we're assuming that the null is true. So we're assuming that that mean is equal to 60 seconds. That goes in the middle. And then we want to label the sample mean on our graph. Our sample mean happened to be this 62.67. So I'm just graphing that over here. That's my X bar. And the question becomes, is that X bar significantly high given that the null hypothesis is true? In order to figure that out, we're going to compute a test statistic T from the standard, or from not the standard normal distribution, but from the student T distribution with the appropriate number of degrees of freedom. So the question is, what is the test statistic that goes with that X bar? In order to find it, we're going to use this formula. So we take X bar, that's our random variable, and we subtract the mean of the X bars, and then we divide by this expression here, which is the sample standard deviation divided by the square root of the sample size. That gives us the test statistic T. Now, here I'm using the exact value for X bar, which is 940 over 15. Then I'm subtracting the assumed population mean. That's the value assumed in our null hypothesis, which is 60. And then I'm dividing by the sample standard deviation, which we calculated with Excel is about 19.481. And I divide by the square root of the sample size. If you do the arithmetic, it turns out that your test statistic T is 0.5301. Now, when we convert to a standard normal distribution, when we look at the z-score, we can say that that's a certain number of standard deviations above or below the mean. Because the standard deviation of the student T distribution is not equal to 1, it's greater than 1. This test statistic T is not a number of standard deviations above the mean, but it is a value of T that corresponds to this X bar. So it's enough to allow us to determine whether this X bar over here is significantly high or significantly low. And very much like when we're converting from a non-standard normal distribution to a standard normal distribution, this area under the curve over here sorry guys, having trouble with my cursor. For some reason it just disappeared. There's my mouse. Okay, this is what I wanted to show you. This area over here, wow, it's just not working right now for some reason. There we go. This area here, so this is the probability that X bar is equal to our X bar or more extreme than our X bar is equal to this area over here. So that's the probability that our test statistic T is equal to our test statistic T or more extreme than that test statistic. So this area corresponds to this area, which means that this probability corresponds to this probability. So when we find out if the test statistic is significantly high or significantly low, what we're really finding out is if X bar is significantly high or significantly low. Okay, so now we have our test statistic and it's going to allow us to make a decision about that null hypothesis. Here, the first method that we'll try is the p-value method. Now, the issue with the p-value method is we need to have access to technology in order to find the area in the tails. And the p-value is an area in the tails. It's a probability. To determine what kind of test we need to use, we need to go to the alternative hypothesis. Since the alternative hypothesis has a not equal to sign, we don't care if our test statistic is significantly high or significantly low. If it's significantly different from the mean, we want to count that as significantly different. So we're going to use a two-tailed test as opposed to a left-tailed test or a right-tailed test. And then because we're using a two-tailed test, we can use the function t.dist.2t in Excel in order to find the p-value. And again, remember what that p-value is. That is the probability of getting a test statistic as extreme as ours or more extreme than ours. So it's this area under the curve. But when we're doing a two-tailed test, we not only want this area to the right of the test statistic, we also want that area in the mirror image on the other side. So this t-score would be as extreme as ours, and t-scores that are lower than that would also be more extreme than ours. So with a two-tailed test, you need this area plus this area. So we use this function in Excel. Let me show you how to do that now. Okay, so we're in Excel and we already have our sample standard deviation right here and our sample mean right there. To compute the test statistic, I just take my mean, my sample mean, and I subtract the assumed population mean in our null hypothesis. And then we divide by sample standard deviation. Oops, let me open parentheses for that denominator. The sample standard deviation divided by the square root. The function for that in Excel is sqrt, open parentheses, of the sample size, which is 15. Close parentheses for the denominator, hit return, and you get that 0.5301, which is just what we had on that slide for the test statistic. Okay, now remember with the p-value method, you need to use one of these three functions in Excel. So go to equals, start typing t.dist, that's for the student t distribution, and then you've got these three functions on the list. The first one is giving you the area to the left of the test statistic t. The second one says t.dist.2t, that's for two tails. That's going to give you the area in the nearest tail for your test statistic, and then it's going to double it. So that's what you use for a two-tailed test. And this one with the RT at the end, that is the area to the right of the test statistic. Since we're doing a two-tailed test, we want this one. So choose that one. And then it asks for the t-score, which is this value here, and the number of degrees of freedom. Since we had a sample size of 15, we've got 14 degrees of freedom, close parentheses, and we get this. So our p-value is 0.6043. And what that means is that the probability of getting a test statistic like ours or a test statistic that is more extreme, either on the right or on the left, is approximately 60%. So we have a 60% chance of getting a test statistic like ours or a test statistic that is more extreme than ours. That's a pretty high percentage. So what that's saying is that this is likely to happen just due to chance, given that the null hypothesis is true. Since this is likely to occur due to chance, then we'll say there's no reason to assume that the null hypothesis is not true. So we're going to fail to reject the null. Now, typically, we take this p-value, this probability, and we compare it to the significance level. That's what we have decided will be our cutoff for what we're going to consider to be significantly high probabilities or significantly or insignificant probabilities. We're going to compare that 60% to the 5% in our significance level. Obviously, 60% is more than 5%. So we're going to say this event of having a test statistic that is as extreme as ours or more extreme, which corresponds to the event of having an X bar, a sample mean, as extreme as ours or more extreme, is very high. It's 60%, and it's definitely high relative to this significance level of 5%. So we're not going to accept the null hypothesis, but we're going to fail to reject the null hypothesis. So what we're saying is the null hypothesis might be true because chances of getting a test statistic like this are pretty high. This could easily happen due to chance. There's a 60% chance of this happening just due to chance. So there's no reason, no evidence that suggests that we should reject the null. Okay, so that's one way of handling it. The other way of handling it is to use the critical value method. Now, this is the method that I would use if I didn't have access to Excel. So if I'm taking an exam and I'm not able to use my computer and I want to make a decision about the null hypothesis and I've got table A3 with me, I can use table A3 to identify the critical values of T and compare my test statistic to the critical values or compare my test statistic to the critical region and use that to make a decision about the null hypothesis instead. So again, we need to start by determining whether we have a two-tailed test or a left-tailed test or right-tailed test. Since the alternative hypothesis has that not equal to sign in it, this is a two-tailed test. We've got 14 degrees of freedom. So now if I want the critical values, I'm going to go to table A3. Okay, so this is table A3. And in order to find the critical values, we need to think about the area in the tails. Since we've got a two-tailed test and our significance level is alpha equals 0.05, we want the area in two tails to be equal to 0.05. So that means we are in this middle column right here. These are all the critical values of T associated with this number of degrees of freedom. So we are interested in 14 degrees of freedom because we had a sample size of 15. So you just look at where this row aligns with this column and you've got your test statistic right here. Now, since it's a two-tailed test, T equals 2.145 is that top critical value. And due to symmetry, the bottom critical value is T equals negative 2.145. So we've actually got two critical values this time, plus or minus 2.145. Okay, so now that we've got our critical values, we can look at our test statistic, which is this 0.5301, relative to the critical values. So our critical values were T equals 2.145, which is right there approximately, and T equals negative 2.145. So if this is T equals 0 right here, this is T equals 1, 2, there's 2.145, and then we want to go negative 1, negative 2, negative 2.145 would be over here by symmetry. The critical region is the region in the tails beyond those critical values. So there's my critical region on the left, and we've got the rest of the critical region is on the right. And the question is, okay, well, where does the test statistic lie relative to those two critical values and the critical regions that I've just sketched? Well, the test statistic is not in the critical region. It's right here. It's in between those two critical values, negative 2.145 and positive 2.145. Since our test statistic is not in the critical region, we're going to say that test statistic is likely to occur when the null hypothesis happens to be true. It could easily occur due to chance when the null hypothesis is true. So we will fail to reject the null in this case. Another way of handling the same thing is to look at the absolute value of the test statistic. Since the absolute value of the test statistic is less than the absolute value of the critical value, that means that test statistic is closer to 0 than the critical value is. That means it's in between those two critical values. Whenever that happens, you fail to reject the null as well. Okay. So we've made a decision about the null hypothesis. Either using the p-value method or using the critical value method, we will fail to reject the null hypothesis. And now we want to state our conclusion about the original claim in non-technical terms. Now remember, our claim was that the population mean is equal to 60 seconds. So that means that the claim is the null hypothesis, and we are failing to reject the null hypothesis. If the claim and the null hypothesis are the same thing, that just means that we're failing to reject the claim. Or in other words, there is not sufficient evidence to warrant rejection of the claim that the mean estimate is 60 seconds. That means when those students were guessing how long 60 seconds were, they were pretty good. They were. We don't have enough evidence to suggest that they were far off from that 60 seconds. So that is how we state our conclusion about the claim. I know it seems like there's a double negative there, and there is. That's because the claim happens to be the null hypothesis. So we're saying there's not sufficient evidence to warrant rejection of this claim. All right. So that was the p-value method and the critical value method. Now we're going to talk about the confidence interval method. With the confidence interval method, we need to make sure that the requirements for using a normal distribution to the sampling distribution are satisfied. So we just need the sample data to form a simple random sample in order for that to be true. And then the requirements for normal approximations need to be met. So either the original population has to be normally distributed, or the sample size is greater than 30, or both of those are true. That just means that the sampling distribution of the sample means is approximately normal. And then we're going to say, okay, let's compute a confidence interval using the formulas that we talked about way back in chapter 7. Whenever we found confidence intervals for the mean, when the population standard deviation was unknown, we did this. We said that the mean is equal to the sum of the x values divided by the sample size, and the margin of error is given by this t sub alpha over 2, which depends on alpha. And remember, alpha is associated with that confidence level of our confidence interval. That's giving us a critical value of t. And then we multiply by this s divided by the square root of n. Notice that this is the same expression that we use in the denominator for that standard deviation, that approximation to the standard deviation of the distribution that we used when we computed our t-scores in the first place. So we're taking a critical value of t, and then we're multiplying it by this estimated standard deviation, s divided by the square root of n. And that's giving us our margin of error. Okay, so after you've computed that interval of values, we're going to say we're 95% confident that the true value of the mean lies in that range, or 90% confident, or something like that, depending on the value of alpha. We're going to make a decision about the null by looking at that interval and seeing whether the value of the population mean in our null hypothesis is in that interval. If the value of the mean assumed in the null hypothesis is in the confidence interval, we're going to say the sample data suggests that the null hypothesis might be true. It might be possible that the mean is equal to 60 seconds, for example. So if that's the case, if the value of the mean assumed in the null hypothesis is in the interval, we're going to say the null hypothesis might be true, so we fail to reject the null. Now, if the value of the mean from the null hypothesis is not in the interval, then we're saying, well, that mean is relatively rare. So we're going to say that that null hypothesis is unlikely to be true. And so we're rejecting the null. And then we'll state our final conclusion in terms of the original claim. Now, actually, let me go back to that statement. I may have misspoke there. Let me restate what I just said. If the mean from the null hypothesis is not in the confidence interval, what we're saying is that null hypothesis is not likely to be true. That range of values that we have in the confidence interval is a range of likely values, or what we're considering to be likely values of the mean. Any of the values in that confidence interval could be the actual value of that population mean. If the population mean in our null hypothesis isn't in the interval, we're saying, that mean from the null hypothesis is not one of the values that we expect to get. So we're going to reject the null hypothesis in that case. And then we want to state our final conclusion in terms of the original claim in non-technical terms that everyone can understand. Excuse me. Okay, so let's go back to the same question that we were looking at before. Here we want to use the 0.05 significance level again, and we're testing the claim that the times from these times are from a population with a mean equal to 60 seconds. So everything is the same as it was last time. The only difference here is that we're using the confidence interval method to test the claim, rather than using the method, the p-value method or the critical value method that we talked about earlier. So we always want to state the null and alternative hypotheses. Those haven't changed. Then we need to determine whether the test is two-tailed or one-tailed and find the area in one tail. And then we'll use this to infer the confidence level. Well, the area or the alternative hypothesis has a not equal to sign, so we're going to use a two-tailed test. That means the area in two tails is equal to our significance level of 5%. So that means we have a 95% confidence level. We've got 5% of the area in the tails. We want the 95% of area in the middle for our confidence interval. Then in that case, T sub alpha over 2 is the t-score that separates that top 2.5% of the area under the curve from the bottom 97.5% of the area under the curve. Now notice that that is equal to the critical t value that we used in the critical value method of 2.145. That's not a coincidence. Then we're going to take that t value, that critical value, and we're going to multiply it by this estimated standard deviation of the sample standard deviation over the square root of n, which is equal to this, which is approximately equal to this. And then I just added the x bar in here. Now to get the upper and lower limits for my confidence interval, I just take the sample mean and I add and subtract the error, and I get these values. So that's telling me my population mean is somewhere between 58 or 51.88 and 73.46. Or in other words, we're 95% confident that the true value of the population mean lies between 51.88 seconds and 73.46 seconds. Now we're going to use this to make a decision about the null hypothesis. Remember, the null hypothesis was that the mean was equal to 60 seconds. Since a mean equal to 60 is in the interval, then it's very possible. It's possible for the mean to be equal to 60 seconds. The confidence interval suggests that it's possible. So we're going to fail to reject the null hypothesis in that case. So we're not saying the null hypothesis is definitely true, but we're saying that it might be true. The fact that 60 seconds is in the interval suggests that it might be true. So we'll fail to reject the null, and that means we want to say this about the original claim. Since the original claim was that the null hypothesis or since the original claim was the null hypothesis, we're going to say that there is not sufficient evidence to warrant rejection of the claim the mean is equal to 60 seconds. Okay, so I want you to see here that when you're testing claims about means, the confidence interval method, the p-value method, and the critical value method are all equivalent to each other. This is different from equivalent methods that we discussed when testing claims about proportions. When testing claims about proportions, the confidence interval method did not necessarily give you the same results as the other two methods. But when we're testing claims about means, all three methods are equivalent. This is because when we're using the p-value method or the critical value method, we're using this test statistic t that is computed with that estimated standard deviation of s over the square root of n. Well, that's the same estimated standard deviation that we used in our confidence interval method. Also note that the t sub alpha over 2 that you're using in your confidence interval formula is the same as the value of the critical value of t. So when you compute those areas in the tails for that critical region associated with that critical value of t, well, that's going to be the same area in the tails that is associated with the t sub alpha over 2 in the confidence interval method. So one way to think about it is in terms of pictures like this. So for our two-tailed test, our t sub alpha over 2 is that top critical value. Negative t sub alpha over 2 is the bottom critical value. And that is giving us an area of alpha split into two tails. So this is half of alpha, and then this area is half of alpha over here. Now, it's not as obvious what's happening here. This is a sampling distribution of the sample means. So what this is saying is that X bar is between the true population mean, which is unknown, minus this error, and the true population mean plus this error. Notice the error is calculated using that estimated standard deviation of s over the square root of n, and the t sub alpha over 2 here is the same as the critical value of t over here. Here we're saying that X bar is in between this value and this value, and if we take that inequality and we write it a little differently, we can say that the difference between X bar and the true population mean is less than or equal to that margin of error. So it's a little different over here on the left than it is on the right, but because we're using the same t values in either case, the same critical values, and we're using the same estimated standard deviation of s over the square root of n to compute those t values, the critical value method and the confidence interval method are giving you the same result. Okay, so here, when you're talking about the confidence interval method, the p-value method, or the critical value method, all three of them are going to give you the same results. Now that's only true for sample means, not sample proportions. So you want to make sure you keep track of the difference between those two when you see conceptual questions about this on your exam. With proportions, the confidence interval method gives you a different answer than the other two methods. But with means, they all give you the same answer. Okay, now there's one other thing I wanted to mention. I'm not going to go into too much detail about this, but it's mentioned in your book, so I wanted you to be aware of it. If you don't have access to technology, you can use table A3 to infer a range of values that must contain the p-value. Now, you also want to keep in mind that the t-scores listed in table A3 are always positive. So if you're looking at a left-tailed test, you have to multiply it by -1. But that's fine. That we've been doing that all along. Now, I'm not going to show you how to identify a range of values containing the p-value using table A3. I would rather you use the critical value method if you don't have suitable technology along with table A3 rather than identifying this range of values containing the p-value. But I wanted you to be aware that this is possible. And if you're interested in using um, the p-value method with table A3 by identifying a range of values, you can check out the examples in the textbook that are associated with this. But again, I would prefer that if you don't have technology, you use the critical value method as opposed to the p-value method. And if you look at that example in the book, you'll see that using this range of values is going to give you the same answer either way. So either way is fine.